So welcome everyone. I'm going to give a few minutes so other people can join. I can see here we have 16 person on the chat watching our stream. Just give a few more minutes so we can start. So again, for those who are there, if there is anyone who didn't receive the link for this stream and got it from somewhere else, please say on the chat so we can include you in the mailing list and for future references as well concerning this webinar series. And for those who are here for the first time, welcome. I am Sergio, your host, and this actually was born as an idea from a group of friends in our free time during to this unfortunate coronavirus situation and global pandemics. We decided to do something, and as it became a trend, everyone is doing webinars right now. So we decided to do this grassroots level, very basic archaeometry webinars online. So people interested in the topic could follow and learn a bit more about this interesting field, which is rather unusual. So the application of sciences, applied sciences, towards archaeology. Yeah, good call, Ole. Okay. If the wait would be a little longer, then I would put some music. That's not a bad idea at all. So, okay, it's 4 p.m. and 3 minutes here at Central European Time. Okay, so let's give it a go. So once again, I am Sergio. For those who do not know, since I didn't introduce myself last time, I am a mechanical engineer and a master in material science and technology, and a master in material science and technology for the application for the conservation of cultural heritage. And currently, I'm pursuing my PhD in archaeological material science, let's say. Good morning, Maria Isabel. Good morning, Abraham. Good morning, Ole. So, okay, today we are going to talk about metals. I'm going to give you this basic talk about metals, introducing what are metals and how we can approach them. How can we... Good morning, Adita, Roshan. See you are all in the chat. So, how we can approach these materials, how we can study them, what questions can be answered, and how we get to those questions, those answers. And later on, after this presentation, I'll give space to a quick, it will be open to discussion, so a quick talk. We can talk about any doubts you still have. And I will keep on reading the chat. So if you have any doubts during the presentation, please type in there and I will try to answer. And afterwards, we are going to have a talk by our guest, Sri Dada, about stones and biodegradation. Okay, so metals. What are they and how to study them? I will start with a very basic definition of metals from a material science perspective. So, materials in this group, metals, are composed of one or more metallic elements, and often also non-metallic elements, in relatively small amounts. Atoms in metals and their alloys are arranged in a very orderly manner, and in comparison to ceramics and polymers, are relatively dense. With regard to mechanical characteristics, these materials are relatively stiff and strong, yet are ductile and are resistant to fracture. So here we face some definitions that we are going to address later on. Alloys and ductility and fracture. So these three concepts are very important to understand what makes metals different from ceramics and plastics. To begin with, this picture here, if you can see my cursor in there, I don't know if you can see my cursor. So, but these structures where you can see iron and carbon, they are very orderly arranged. And this is a key feature in metals. So what is ductility and what is fragility? Materials absorb energy and they fracture when they cannot withstand more energy. more stress. Ceramics are known for being very strong, very rigid, very hard, but they are not ductile. They just crack abruptly. They do not give you a sign they are going to fail. They just fail you. Metals, instead, they start deforming at a certain point after absorbing a certain amount of energy. They have this capability of absorbing energy until it's fractured. And as you can see, plastics are not part of archaeological materials yet, but they can absorb a great deal of energy, elongating. Like, who never pulled a piece of plastic and could see it? I forgot the English word for that, but you can pull it and it will elongate significantly. So the other point that we saw was alloys. What is an alloy? The definition is a metallic substance composed of two or more elements. And in the definition of metals, we saw that they are usually composed of one or more elements. So the vast majority of metallic artifacts, or metals, they are alloys, not made of alloys, that's a typo. They are alloys. Here on the right corner, I put this little scheme where you can see on the vertical axis the temperature. So the higher you go, where you have this D, or this green ball with L, which represents a completely molten fluid. This is like all liquid metal. This scheme represents an alloy composed of copper and tin. As you go down in temperature, as you cool your material, you can see the formation of phases. We will use this word a lot from now on. So the phases are characterized by a certain distribution. How these elements start cooling, they start arranging themselves. We saw that metals are very orderly manner, are arranged in a very orderly manner. And depending on the composition and how they were cooled, the phases will change. They can precipitate, they can present different arrangements, and this is very important to understand how they were produced, and we will get there. In archaeometallurgy, the branch of sciences that studies metallic artifacts, there are a series of things we can study and analyze to better understand craftsmanship and how these metals were produced in the past, how past civilizations utilized and dealt with metals. The first big branch, I separated them into different categories, are waste products, which are mostly flux and slag. They originate from the smelting process, which we are not going to talk about in this presentation, which can also be analyzed to understand the chemical composition, where the ore came from, and the capabilities, the technological level of a certain society. We can study the tools, molds, crucibles, tongs, whatever you imagined it was used at the time, like bellows, how these things were used to craft metallic artifacts. And obviously, the finished products. And we are going to talk about finished products here. We are going to see how we can analyze them, what answers can we get from it, with which techniques, and I'm going to talk into more detail about the techniques later on. We can analyze these products, these metallic artifacts, from a micro and atomic level, and from a macro perspective. The macro perspective, well, obviously you can see it with the naked eye, and you can get some answers from that, mostly concerning corrosion, because that's the most superficial strata layer of your metal, your object, and you can see different hues of corrosion, and they represent different things. In a macro and atomic level, you can study the chemical composition and the microstructure of the metal, and these will give you more information, obviously. Moving on to corrosion, what is corrosion? Corrosion, by definition, and I love these definitions, is the deteriorative loss of metal as a result of dissolution and environmental reactions. So you can see that the metal, the artifacts, they interact with the environment, be it the burial, the soil where it was buried, the burial site, or no, not burial site is not correct. Pardon me, I'm not an archaeologist, but I'm trying to get my way there. So the soil and even the atmosphere. So for modern art, for example, you have huge problems with artworks being exposed day and night to harsh environments, to rain and sun. So they interact with the environment, and this can tell us so much. You can see on these pictures here. Well, what do you think here? In the right picture, on the B figure, is the boundary, the original boundary of your element, of your metal. Well, it is not this clear metal in the center. It's actually this very thin layer. You cannot see my cursor. Okay, that's a pity. But you can see that the bulk metal has an outer corrosion layer to it. Then you can see the boundary of the original metal, and on top of that, another corrosion. And there are so many colors in that. It's like a mosaic. It's very nice to see. You have many, many colors, and these colors represent different things. Corrosion occurs differently depending on the soil and the alloy compositions. This is very important, and I will tell you why. Why does corrosion occur? I like to keep this question here because this is asked often. And generally speaking, not to get into electrochemical details, which I'm not an expert by any means. So generally speaking, it is just the metal trying to go back to its natural state. So we know that these artifacts, these finished artifacts, they are heavily processed. The original material, the raw material that gave birth to this artifact, this finished artifact, if we are not talking about native copper, which is another topic, they were mined and they were smelted, they were heated, they were molded, and they were worked on. So there is a lot of things happening onto this raw material until it gets to its final shape. And nature tries to put the metal back to where it came from. It's a stable form, so it's oxide form most of the times. So it's the metal always trying to go back to its natural state. Why do we study corrosion when talking about ancient artifacts? Okay, I will check the chat just a minute. You can find Vitreous lags in the metals metal. Yes. Ola added a point here that you can find vitreous slags at metal smelting facilities during excavations. This is true, and some of these vitreous slags, they originate from the smelting process, which you add flux, and sometimes you have silica on the ores, and the flux task is to actually take off some of the impurities from your ore in the smelting process to purify, and so you can get the metal from the ore. And he also, okay, there is a question from Ola here. Why do we have the stratigraphy? Okay, this is stratigraphy. I will go back just a minute. This is stratigraphy here that you can see on figure B, better represented, is a series of successive oxidation states of copper in this case. The metal is made of a copper alloy. And the first oxidation state of copper, if I remember it correctly, it's cuprite. Cuprite, I think, yeah, copper oxide 1. Correct me if I'm wrong. Then successively, it will further oxide and turn into tannerite, another compound, which is the second state of oxidation. And it also depends on the soil. If you have an acidic soil with rich in chlorine or rich in sulfur, so it depends. And these reactions will create different layers through time. Guys, please don't be shy to ask questions there on the chat. I'm here to answer them, and if I'm not clear. So, moving on, I was saying on why do we study corrosion? So if we study the chemical composition and the microstructure of the corrosion layer, we can get information on the provenance. Yes, sometimes we can, and I'll explain why. We just said that the environment reacts according to its composition and the alloy composition. So if you have artifacts with unknown archaeological background, they just came from the black market, you have no idea where they came from, where they were excavated. All you can do is do some iconographic studies, maximum, or check the chemical composition of the alloy to see if it matches another group of metals. But analyzing the corrosion, if it was not removed or cleaned, you can verify if that corrosion belongs to a group of corrosion products of known artifacts. Let's say we excavated a site A, and in that site A, where you excavated, you know all the metals came from there. It is certain because you dig it. Then you study that chemical composition and microstructure of those patinas, those corrosion layers, and you see there is a pattern because of the soil there and the alloys composition of that workshop. If you analyze a material, an artifact that you do not know where it is from, and you see that the chemical composition and microstructure of that corrosion layer matches that one, Well, that's not for certain, but you can start thinking that that object could belong to somewhere around there. So this is very important. So the corrosion actually is part of the object's history. It should not always be cleaned. I will get into the conservation part, but it should not always be cleaned since it is part of the object. This is a very dangerous discussion, I would say. There are people who defend that it should be cleaned and removed, and people who say that it should be left there and treated, because it is part of the material's history. And most important, I guess, and the most widespread application of corrosion studies is for conservation purposes. When you understand the corrosion mechanisms, you can prevent them from further damaging your metal. Once you take an object from its equilibrium position, where it was buried by a couple millennia, it will be shaken a little bit. Like you were there in a cave for thousands of years, and all of a sudden you see the bright sun outside. You will react to that. You will be like, wow, what the hell is going on here? And then you disturb your material, and it will start degrading, and some things will happen to it. And if you understand how corrosion occurs, you can prevent this from further damaging it. And also to control the environment where you leave your material. In a museum, control humidity, control the atmosphere. So this is very important. I'll just go very briefly here because we already spoke more or less about these things. So the environment interacts with your object, and depending on the alloy composition in your environment, you will have the formation of different structure types of corrosion. So this scheme will help us understand the next steps, the next topics we are going to talk about. So you can see now a scheme instead of that real picture of a corroded bronze, a section. So this material was cutted, this artifact was cutted, so you could understand the stratigraphy. And you can see in the first one a heavily corroded metal with the core intact, so you still have metal in there, it's not mineralized. Then you have a corrosion layer product, then you have the outer corrosion layer product. The second one, you can see that there is not a definite boundary between the core of the metal and the corrosion layer, the internal corrosion layer. It's all mixed, it's all a fuzzy mess. And in the third one, you see the patina, the noble patina. That is a stable corrosion product layer that protects your metal, that prevents your artifact from further corroding. So that's why it's called a noble patina. All of these apply mostly to bronze products, bronze artifacts, since the corrosion mechanism in iron-based products are quite different. They are more aggressive, and they have another name. We call them rust. So they are very, very aggressive, and when you clean, they will just form over again, and you clean again, they will just form again until they eat the whole metal. So why is it important to know that there are different layers in your metal, in your corrosion layers in your metal? Because they have a different chemical composition from the bulk metal. Why is that important? If we want to analyze the chemical composition of an artifact, which is a very routine analysis, it's very common. It's been going on since 1964, as far as I recall, from studies, of course. I'm not that old. And then you can see here on this right picture, this is an arrow showing, you can see the direction. Okay, here in the upper, it's so sad that you cannot see my cursor. So in the upper part, it represents the 0 point on the graph below, and the arrow goes down. So you can see the chemical composition changing as you move on to the outer part of this picture, so to the frame, to the border. You can see that copper concentration, this upper line here, the red line, I guess, it decreases significantly once it reaches this darker part, which is the corrosion layer. When you do chemical analysis, going back to that discussion, you will get 99% of the times information on the surface. So this chemical composition that you measured and you assumed it is the chemical composition of the object, in fact, it is not. It is representing the chemical composition of the upper layer. It does not necessarily mean that that composition represents the bulk metal. This is why some of the chemical composition analyses are done on sectioned metals. But for that, you have to cut your material, you have to sample it. We have a question here from Ole once again. Thank you, Ole, always participative. So he's asking, what is the bronze disease? Good you touch on that topic. Bronze disease, I'll go back here because I have a picture of that. Bronze disease is a type of pitting corrosion, and it is a cyclic corrosion mechanism promoted mostly by chlorine. Chlorine is very aggressive to bronzes, and once it cracks the metal and gets inside of it, cracks that outer noble patina layer and manages to get underneath that, it fuels a cyclic process, creating anions that further react with the environment, that create more chlorine anions that enter the material and create more anions that will react with the environment, and it just goes on. So you can see these black dots spreading throughout the surface of the object. There are ways to stop that and to treat bronze disease, but this is the most aggressive corrosion that you can find in bronzes. As you can see, the detail on this picture on the left, it is literally an open crack on the material surface. This is one very small pitting corrosion. This image was taken with an SEM, scanning electron microscope, and I'll get into more detail further on. Okay, so now we are going to talk about chemical composition and then metallography. So for chemical composition, it is important to understand what are major and what are trace elements. Trace elements, I just put this picture here so you can remember. Trace elements are literally like a drop in the ocean. They are there in 1/10 of a million sometimes. They are in very, very small concentrations. And as you can imagine, if you want to detect them in your material, you need very sophisticated high-end instruments. Major elements can be detected with less sophisticated techniques, such as X-ray fluorescence that we will talk about in a minute. So this is the big difference. Major elements, they are present in a majority, usually above 1%, and trace elements are there in a very, very small amount. These trace elements are important, and I will say why. When analyzing the chemical composition of your metallic artifact, there are certain ways of doing that. Now we are getting into the techniques. So I'll talk about the ICP-MS and TR-XRF. What does it mean? ICP-MS stands for Induced Coupled Plasma Mass Spectroscopy. It's a very complicated name, but what it does, it just measures the weight of atoms, as simple as that. And because it can measure the weight of atoms, it can measure isotopes. Isotopes are nothing more than atoms, like the same atom, of the same chemical elements, with different weights. So you have two atoms of copper, one is heavier than the other. Total reflection X-ray fluorescence, it's a very unorthodox technique, let's say so. I have never seen any study using it for archaeometallurgy or archaeological purposes at all. If someone has it, please link it in the chat. I will be very pleased to read it. The difference between these two is that ICP-MS is a destructive technique, so you have to sample your material, and the sample is destroyed after the analysis is performed. The other one is just invasive. You still have to sample, your material, but the sample can be used. That old plate that is sitting there in the lab for 20 years, it can be re-examined, if you wish so. So this is a big advantage, because if you want to sample it, if you have to take a sample, a piece of your priceless artifact, you want it to last at least, so the study can be repeated when you have more sophisticated mathematical models and techniques. These are the big differences between these two techniques and the other two, SEM-EDS and XRF. SEM-EDS, we already spoke about, it's scanning electron microscopy. The EDS is just to say that it has an energy dispersive spectrometer coupled to it, so it can get chemical information. It's a microscope with something that can read chemical elements. And XRF, it's X-ray fluorescence. So it reads atoms as well. It cannot detect the weight, but it can count atoms in there. That's basically it. These last two, they are non-invasive. Non-invasive at all. You can just take your object, shove in the machine, press play, take some results, take it out, untouch it. You can also cut your object if you wish so, or take a piece of that if you want to look into more detail. So if you want to look at the microstructure, as we are going to speak in a minute, and if you want, again, to get information on the bulk of your metal, if you want to take the composition, of the bulk of the metal, you can cut it. but there are ways to go around it. Roshan added a point here. I think that must be noted that ICP-MS is only microinvasive with laser ablation. Yes, it is microinvasive, but still, that tiny piece you sample is gone forever. You ionize that all. But there are many variations of the technique, and I just didn't want to get into much detail. But you are right. There are many variations to the techniques. Also, how you measure the weight of your atoms. There are quadrupoles, different types of quadrupoles, and many whatnots. But in sum, I just wanted to be very basic. So an overall view of what you can do. Why do we study chemical composition? So moving on. With chemical composition, you can establish trade routes, interactions between societies, and try to trace back a piece of metal to a certain origin. As we said, for the corrosion, since each soil has a different composition and different properties and how they interact with the samples, the mines, they also have different properties. So you have mines, for example, in Sardinia, which are rich in malachite, azurite, pyrite, chalcopyrite. I wrote down some of the names because I cannot memorize all of those. What that means is that the ores from this region, they are typically rich in bismuth, antimony, Sb, lead, and iron. So these are the impurities that you can find in ores from Sardinia Island. So if you found an object in Etruria, and it is rich in bismuth, and by rich I mean, again, in the trace amount, okay? So it's a couple hundred parts per million. It's a very tiny fraction. And you see they are rich in bismuth and antimony, and they have a little bit of iron, around 1 or 1.5%. You can infer that maybe it came from Sardinia because it fits the ores from there. So it could have been, the raw material could have been extracted from that site. So this is one of the reasons we study chemical composition. And remember I said about what I said about isotopic ratios. You can do this traceback in a similar way to isotopic ratios, to regions that you have already mapped. So this is a very experimental, new technique. People have been doing the lead one for quite a while, but in very specific regions and contexts, because for that you need a database. So as you can see in this map, you have different values, ranges for different strontium ratios. So in this region here in the upper north, in Golan Heights, you have from 0.7448 to 0.70767. So if you find in your instrument a lead strontium isotopic ratio similar to this one, and you think that your sample, it's plausible that your sample came from this region, then you may associate the raw materials to this region. But you need a database again. So you need to know what you're comparing it to. Another thing that you can do with chemical composition analysis is studying the distribution of species on the surface of your material. So why do you do that? To study corrosion. To study corrosion products and how they are distributed on the surface of your metal. This is not common, but with that you can see inhomogeneities in your metal, and I will get why inhomogeneities are important. Chemical composition using X-ray fluorescence, this is just a parenthesis I want to make, and if anybody is interested in this topic, please leave a message in the chat, and then we can discuss it later on. You can get information on the bulk material of your corroded metal without sampling and cutting it in a complete non-invasive way. I just put it here because I worked with that, and it's very important to highlight that there are ways to get through this corrosion layer, get the bulk information without damaging the artifacts. So there are some sophisticated mathematical models that you can simulate the interaction of X-rays with matter, and according to the parameters you gave to your computer, you can extract what is there in the bulk and in the corrosion layer. It's an iterative, time-consuming process, but it is feasible. So we will move on to the last part, which is metallography, and my favorite one. So metallography, you study the microstructure of your metal, and this will tell you how it was made. This is fantastic. Like, you can imagine the smith hammering metals and then putting them back in the oven or quenching them in cold water, and you can see all of it by looking at the microstructure of your metal. I put here a parenthesis on neutron analysis because this is rather unusual. I'm talking about most of the general picture here, but I also like these curiosities, these particularities. So with neutron analysis, you can see the formations on the crystalline structure of the metals. Crystalline structure, we spoke about it in the beginning. Metals are very orderly arranged atoms. So they have a perfect organization inside. They're almost like a grid inside. And when you hammer it, when you strike it, when you bend it, there are some deformations that are made there that are sometimes not irreversible, but you can look for them. This is a work I saw it for the first time in 2017 in this Tekanat conference, that a group of researchers used neutron analysis to see the distortions in this helmet's in armor's grid, not the helmet, but they also did in the helmet later on, to see the armorer's mark. In medieval armors and weaponry, the craftsman, the smith, would add a stamp telling that I made this, so this is from my workshop, and they would hammer it on the surface of the object. By extended use and polishing and usage and polishing, that armor's mark would just fade away. And some of them are faded away. And they tried to use neutron analysis so they could still see the distortions made by this hammering 500, 600 years ago on the metal, that it is still there. And with that, they could recreate these armorer's marks. It's a very interesting work. If you want to check it, please check it out. It's completely worth the while. So moving on, microscopy and etching. So how do we analyze the microstructure and what can it tell us? Let's go to craftsmanship, how we made what we made. First off, we have to understand few terms to understand heat treatments, how they work, and how we modify our metals. First of all, defects. These are very important when it comes to metals. Metals have defects, and that's what makes them what they are. That's their fingerprint. Okay, not in that sense of characterizing them, but it is an intrinsic characteristic of metals. Then we will look at the continuous cooling transformation curve. It sounds very complex, but believe me, it's not. It's just for you to understand how the metal changes according to time and temperature. So we all have seen in movies a smith taking a sword out of the oven, like smoking hot, and putting it into a pool of water or oil to cool it down. And we will see what it does to the metal. Before moving in there, I want to add a parenthesis on bronzes, because now we are moving on to the realm of steel and iron-based artifacts. So because of solubility problems and also because of melting temperatures, when you have too much lead in bronzes, they will precipitate. These pictures show you islands of lead in a sound copper matrix. Why does it happen? This is a defect. Remember, I just said what about defects. This is a defect. And when you have these, your material becomes very brittle. It becomes very brittle because defects, they act as a barrier for the propagation of stress. So this cute little image here with the caterpillar shows you the motion of defects inside the metal crystalline grid. So see this line that ends abruptly in the middle of the crystalline grid, this one with darker balls. When you apply stress to the metal, this is called a discordance, just for a fact. It will move on inside the crystalline grid. So it absorbs part of the energy that was applied to the metal and moves on. If you have a 100% crystalline, sorry, not 100% crystalline, monocrystalline metal, which means it is just a big crystal, you will see the bumps on the surface after you apply some stress to it, because the defects inside the matrix, they propagated. They had no other boundaries to change their direction. They were just moving on since it is just a big crystal, and they reach the outer surface, creating these bumps. Monocrystalline metals and materials do exist. In ceramics, pores act as defects, and the more porous your ceramic is, the more fragile it is, because it will restrain the propagation of stress. This will absorb energy, and pores, they act as concentration of tension. So once that stress reaches the pore, it will just crack open, and the crack will propagate. And again, defects are barriers for the propagation of stress inside the metal. The more defects you have, the less energy the material can absorb, so it becomes more fragile. And then you have the transition from a ductile material, which we spoke in the beginning, to a fragile material. So your metal will just break abruptly. Imagine a clip, a paper clip, a metal paper clip that you keep on flipping, not flipping, but bending, that you keep on bending. You will bend it so many times that at one given point, it will just break abruptly without giving a notice. So you're putting so much stress inside the metal when you are bending it that you're creating defects inside the metal, and those defects will hinder the propagation of further stress you're applying to it. To a point, it will just break and crack. So when you work the metal, when you're hammering it, you introduce defects. You're always creating and putting defects inside the metal when you're stressing it. Hence the example with the paperclip. So if you do not relieve this stress, the resulting object will be very fragile. And you do not want your spear to shatter when you strike a false shield, do you? Or your sword to shatter. You will be unarmed for the rest of the fight, and you will just probably die. So you want a good quality metal. You want a metal that it's ductile, it's stiff, and it's very strong. And that's where comes the capacity and the technological level, the skill of the weaponsmith. That's why you have fancier swords like king swords with adornments and with a very good metal, and you have those cheap ones that can shatter at any given minute. This is achieved, a good quality metal is achieved by heat treatments. It is a series of operations performed to the same object during its final crafting stage. So you're applying heat to it, you're cooling it, and then you're giving and taking heat, and then hammering once again until you reach the state you want, the perfect state you want. There are a few things we need to understand. It sounds complicated, but I swear it is not. There are a few things we need to understand before moving on. One of them is the recrystallization temperature. I showed you the grains, the boundaries where stress propagates. The grain boundaries, I will go back on that slide just to refresh. So here, you have these grain boundaries. Grain boundaries are defects, so they will absorb a lot of energy when you're putting stress into your metal. And these are the preferred propagation path of defects. So if it has to crack, it will crack there. So the recrystallization temperature is the temperature at which recrystallization, what's such a difficult word, just reaches completion in 1 hour, which means all the work, the hard work you put into your metal to shape it the way you want it, if you give it too much heat for 1 hour, it will just become one big crystal without any mechanical property usable, a useless piece of metal that you will have to rework once again. And the critical temperature, which is the boundary temperature in which the alloy will change phase. Remember the word phase that we spoke before. So according to the cooling rate, how you cool your metal, different phases will be created. You can see on this graph on the right, all these lines represent steel. These are all steel materials with different crystalline structures. And the vertical axis represents hardness. You can see that this one called martensite, it's extremely hard. Way harder than tempered martensite, which is tempered is just it was heated again once it was worked. And then fine pearlite, which is another phase of steel. So you can see the different phases have different hardnesses. And how do you achieve them? This is the secret of the craftsman. He knows or she knows how to work the metal until it reaches that fine structure he or she wants. So you have a very good quality material. And you can look at this TTT curve or a CCT curve. It has different phases and temperature and time here. And then you have hardness. So the cooler the faster you cool it, the harder material you will have, the harder phase you will have, but it is also brittle. Remember, you are introducing a lot of defects in your material if you are cooling it too fast, too quick. Then you can reheat it once again to relieve a little bit of stress and make the crystals and the grains, make the crystals grain larger so you have less defects. So you are relieving a little bit of the stress. So you have a more ductile piece with martensite structure as well. So this is a very good steel. Another phase diagram, just forget the middle of it, which is a hell complicated, and focus on the lower part, the bottom part. This represents the phase diagram of a copper tin alloy, which we saw before in the beginning, but in the more brief detail, just the first part. You can see that in the middle one, annealed. So let's look at 10%, an alloy with 10% tin. So in theory, an annealed one with 10% tin, if you look at the microstructure, you will see only this alpha phase here. You have one homogeneous phase. If you do not anneal it, you will, with the same metal, with 10% of tin, at the end of the process, you will notice that there is one extra phase here that shouldn't be there if you have annealed it. So when you look under the microscope, the metallography, like the crystalline structure of your metal, you can tell, depending on the concentration, well, if you did the chemical analysis before, you can tell whether that metal was annealed, how it was annealed, and how it was annealed, if it was at all. So you can attribute certain characteristics to different workshops. I took this image from the work of Joana Gonzalez, and in this work, she was trying to differentiate and attribute different workshops to a batch of metal of unknown origin. So they were looking at the crystalline structure and the chemical composition to try to give these metals, to attribute these metals to certain workshops. And you had groups of metals that were annealed and groups of metals that were not annealed. And with that, she could establish like a pattern, a distribution of these metals belonging to different workshops. So to wrap it up, because I already took way more time than I intended, there are two techniques that are, again, unorthodox, and I love the application of these unorthodox techniques to whatever you want. Like, just take a technique that it's not applied for that, let's try it out and see what comes up. So tomography and radiography. They are not often used for metals. Radiography is slightly more, but tomography is a rather new one. You can use these two techniques on metals as well, with certain restrictions, because metals absorb radiation, a lot of it. So it's very hard for you to get a good quality signal or a result from these analyses when you perform them on metals. Tomography, you can see through the metal. You can recreate it three-dimensionally on a computer screen, and you can see defects on the inside of the material. You can see if there are lead islands in there. You can see how thick is the metal without cutting it, without opening it. You can see through the metal and slice it in any direction you want on the computer. This is really, really nice. And radiography. That's been going on for quite a while. These are very old images of Peruvian artifacts. And radiography was used here to try to understand how these pieces were tied together to the other metal matrix. These are different pieces of metal, various pieces of metals, tied together to a base layer, a substrate, a metallic base layer. And they use this technique to try to understand how the metal was bound there. We have one question here from Ole. Why tomography is unorthodox? Well, it is unorthodox for metals. It is not often used for metals, but for other objects, and especially human beings, it is often used, as we all know. But for metals, it is not often used due to the absorbent nature of metals. They absorb a lot of radiation. So if you have a thick metal, you will not get the signal. So the signal will not go through. You need a lot of power for that. So that's why it's not often used. People use, but it's not often. And with that, I would like to wrap it up. Thank you so much for staying for such a long time, been almost nearly 45 minutes. And I strongly recommend for further reading this book, Material Science and Engineering Introduction. This is like the Material Science Bible. I strongly recommend the 6th or 7th edition if you want to get into more details. And they have a lot of content about ceramics as well. And on YouTube, if you're interested in metallurgy, and yeah, mostly metallurgy, and also ancient one, they do craft some old stuff and recreate some old objects, classical objects like Viking swords, whatever. You just look for this channel on YouTube. It's called Men at Arms Reforged. They changed name for All Me channel, but just look at it. It's really interesting. You'll spend, I surely guarantee you'll spend hours there looking. These guys make an amazing work. And that is it. And if you have any questions, I'm keeping an eye on the chat. Thank you so much, João. Well, meanwhile, I'll try to connect to our guest, Sri Dada Bhattacharya. I hope I spell it right. So I'm trying to connect here. Can you hear me, Sri? Shri, can you hear me?
Yes, I can.
Ah, okay, there you are.
Can
So,
we do the change like
yes, 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 I put it online. I put you online, and I'm going to switch your screen so you can. The screen is yours now. Okay, is this the second presentation? Yes, yes, this is the second presentation. The first one, the link is available, and I will put it on the description of this video so you can access it. And the first one was about ceramics and glasses, and it is available. If you want, I will also leave in the description the link for filling up the Google form so you can have updates on the upcoming sessions, and I can also link you there some material if you want, or we can get in touch. Okay, there is another question from Jonica. I hope I said it right. Could you please explain more about the determination of the bulk without the need for sampling? Of course, I would love to. Okay, so let me go back there. Shri, hold on, we'll go to you on a minute.
that's okay.
You're appearing on there, okay?
Hmm.
So, let's move on. Okay, um, there is a way to get this information with what I call reverse engineering, but it's not that per se. There are very sophisticated algorithms that make use of Monte Carlo simulations that they can perfectly simulate interaction of X-rays with matter. So you give your computer a series of parameters. Like I know my X-ray tube emission spectrum, I know my detector parameters, and then I give it a file with the thickness of the several layers that I think compose my sample, and an initial guess. So since you did an experimental analysis, you need to do one spot analysis at least on your material to get an initial guess. So we'll have a spectrum, an XRF spectrum that you can see here. This is an XRF spectrum. So with that, you can look at it and you're like, there is a lot of copper. I can see some silver here. So I can start guessing what this silver, by the way, is from the tube. It's not that it's present on the. Oh, it's not silver. Sorry, this is tin. This is tin, around 25 kilo electronvolts. This is tin. So you can start with an initial guess. So I know this should be a thin copper alloy at least. So you also have peaks here that should be from iron at around 6.5 kilo electronvolts. So you know kind of an initial composition. And by looking at the sample surface and the colors of the patina, you can guess, oh, there should be a lot of cuprite, maybe some tannerite or Ponianskaya, I don't know. By the colors, you have an idea of what should be your corrosion layer. And then you'll give this information to your computer. So please simulate a spectrum with these parameters that are equal to the experimental ones, like the distance from the sample to the system, to the X-ray source and the detector. All these parameters must be known because they are physical parameters of the experimental setup. You will give all this information to your computer and tell it to run a simulation. It will give you an XRF spectrum back. You will compare that XRF spectrum simulated by the computer with the real one. And then you will see the differences. So you have a higher peak here and there, a lower one here and there, a higher contribution in this region or in the other, and you change your parameters. This requires quite some experience with X-ray fluorescence to adjust these simulation parameters. So that's why it's a very time-consuming process. Then you will adjust these parameters and run another simulation. Then you compare again with the experimental one and change it again if needed. You go on fitting your data manually until you have a match. When you have a match, theoretically, what you told your computer to produce represents reality. Because these algorithms, they are very, very accurate. The errors are about 0.01% sometimes. It depends on the algorithm. There are a series of them. The one I used is the XRMC package. You also have XMISIM, if I'm not mistaken. You have Giant4, Penelope. There are a series of algorithms to produce it. And when you have a match, it means that layer ordering, layer composition, and bulk composition that you told your computer could represent reality. So it has been tested with reference samples, and it works. It's very interesting. Okay, Shri, now you do not have to turn off your link. You can stay on there. So I hope I answered this question. If there are any other questions, please let me know in the chat. Otherwise, we are moving on to Shri's presentation. Okay? Okay, Shri, turn on your mic so we can hear you. Shri?
And I share the screen, right?
Yes, I can see your shared screen. If you put the PPT, I can transmit it to YouTube. Okay, thank you everyone for the participation and the attention. Thank you so much. It's okay. Once you put on the PPT, I will transmit the screen.
Okay, have you not got the PPT? Because I have already put the PPT.
Not yet. I cannot
okay,
see
hold
it
on.
here.
Just a second.
Okay.
Share screen. Now?
Oh yeah, now I can see it.
Yeah. Okay, so I'm good to go?
Yes, you can close my Skype screen over there.
Yeah. Yeah, okay. Just a second.
Okay, there you are. I guess your webcam froze for some reason. In anyways, I'll just take it off then. Okay, you can go on. The stage is yours.
Okay.
Just one.
Everybody.
Okay, sorry about that. I forgot to introduce you.
No.
So rude of me. So Shri, she is Shri Dada Bhattacharya. She is a dear friend and a bachelor in Indian history from Sophia College, sorry. And she has a master in archaeology from Deccan College and a master in archaeological material science from the University of Evora, University of Sapienza, and Thessaloniki Aristoteles Panepistimios. I think that's the Greek name. I don't remember the English one. So go on. Now you can proceed. I will not interrupt you.
Thank you, and thank you everybody for joining. So what I'm going to talk about briefly today is stones and microorganisms, how microorganisms affect stones. So we know that stone is probably the oldest material that has been a part of an expression for humans. It is it remarks cultural growth, aesthetic growth, it gives you history, and also, and what is most important is it gives you a know-how of the economic growth of the time. What we also need to understand is stone is probably one of the most tangible form of cultural heritage, and it's not just used for construction. It's, as you can see on the screen, it's used for many things like statues, uh, some fountain like walls, sarcophagus, and of course the Easter Island. And we need to understand that this has been the preferred medium of expression for a very long time. So now I'm just going to briefly touch upon what kind of stones were used in ancient construction. So you have two basic families, which is the carbonate stone and the siliceous stone. So in the carbonate family, we have limestone and marble. And today I'm going to put more importance on marble and limestone, just because I have had the opportunity to work on them. I have not worked per se on siliceous stone yet. So one very important characteristic that we have to remember about carbonate stone is that they are extremely porous. And just because they are porous, of course, it makes them extremely, how do I say, they can dissolve very easily in an acidic or an alkaline situation, and they will not leave back any residue. The next thing that we need to come to is a basic terminological study. Now, when we say weathering, erosion, alteration, damage, decay, we have heard all these words, but they have very particular meaning. So when you say weathering is basically any kind of a chemical or a mechanical process where the stone goes through where the stone undergoes certain changes, and what happens is it will eventually deteriorate. Again, then when we come to alteration, so after all these modifications happen on the stone, it doesn't simply mean, okay, we cannot use the stone or we cannot make the stone better. So we can make certain alteration, and this is very important from the conservation point of view, to make it better. Okay, and as you can see, so you have images where you can see there is lichens growing, and but on the next statue, because of alterations, it's been curved. Then we come to decay. Decay is any kind of physical modification of the stone property which can lead to its absolute like loss of value. It might erode to such a point that you will not even know what it was initially used for. And finally we come to damage. Damage is a very loosely used term, and it's completely dependent on how someone perceives it, how someone perceives the rate of decay. And the words are intertwined and sometimes used very loosely. Okay, so now you can see how all the four, like this particular image is to show all the things that I just spoke together in one frame. Before I go, now is where I will start talking about microorganisms. Now microorganisms is a large part, but one of the parts that lead to the decay of stones, or say weathering of stones. Okay, so now when we study classification of microorganisms, yes, we all know what bacteria is and fungus is and all this, but how do we divide them? So bacteria and archaea are prokaryotes. So prokaryotes are generally unicellular organisms, and they do not have they do not have a membrane bound nucleus, which is not so for eukaryotes. Okay, but now that's totally going into a different topic, so I'm just going to give this, just remember this slide when I start talking about the next things. You also need to remember microorganisms are divided on how they achieve their nutritional mode. And these are some of the words that you will keep encountering when you do some studies like this: microorganisms, microbiology, biotechnology, biodetergents, biodeterioration, bioweathering, biofouling. Like, the words sound so similar, so it's very easy to misuse these words. So this is just a slide so that I'll give you 2 seconds to see it. Okay. So let me go to the agents of decay. Now what we need to understand is atmospheric conditions and biological agents we can look at it as two sides of a coin. Okay, because they're extremely interdependent on each other. Now we know that the atmosphere has nitrogen, oxygen, carbon dioxide, and this is mixed with certain impurities. And what happens is, when we have combustions, especially through automobiles, what happens is these kind of impurities, they settle down on the stone. Now, in your atmospheric condition, you will also have chemical weathering. So what is chemical weathering? There are various forms of chemical weathering where, the water is going to mix with the impurities and sulfates and carbon dioxide and nitrates, and this will give rise to acidic corrosion. There is also this thing of mechanical weathering. So you have, in atmospheric conditions, you have mechanical weathering and chemical weathering. Again, they go hand in hand. It's almost really difficult to separate the two because one is dependent on the other. What we also need to remember is when we have any kind of atmospheric condition, there is each stone or each stone has a different level of their expansion. So when the stone gets wet, or when it's extremely hot and dry, when it's cold, so the expansion of the stone will differ. And this constant expansion and contraction, what ultimately happens is there will be a detachment of a part of the stone from the bigger part of the stone. The picture that you are seeing right now is a particular formation of black crust formation. Now, when you were talking about black crust formation, okay, there is a divide because a lot of people think that it is a part of fossil fuels, it's a burning of fossil fuels, but a lot of people think it's also because of nitrifying bacteria. Now, and also a part of climate change. But now we have to remember, we have nitrifying bacteria because of the kind of impurities that we have in the air, in the atmosphere, sorry. Secondly, the other thing that we have in atmospheric condition is when you have droughts or when you have floods, you will have a salt crystallization on the stone monuments. Now, this will obviously, what happens is then it gives rise to oxalates. And leaving everything aside, you have the basic problems of, the groundwater, then you have leaking pipes, then you have temperature changes, the wind, the dust, it all comes together to and become as an agent of decay. Now, when we shift to the biological agent of decay, there are these two processes are something that, like, just to know, when you say an assimilative process, it basically means where your material, in this, for example, I take, say, a marble piece, okay? So that is my material, that is my substrate. Now that becomes a source of nutrient for the microorganisms. And in a non-assimilative process, the metabolites that is formed by the microorganism, and that, again, if you can understand, this is a chemical change because there is secretion of oxalic acids, there is generation of carboxylic acid. So it's nothing works on its own. It's a combined effort from the atmospheric condition and biological agent conditions to become agents of decay. Okay. Now, this is exactly what I just said. So you have environment, you have the environmental problems, then you have the material. The material can be limestone, it can be marble, but still what happens is the material will weather. This goes without fail, which in turn provides as nutrients for microorganisms, because a lot of these microorganisms, for example, if you see types of fungi or types of algae or cyanobacteria, these microorganisms actually use the material as nutrients. So once the microorganism starts setting down on the material property, like on the substrate, you can see a physical, visible change. And that is the term that I'd like to introduce, which is biofouling. Biofouling is nothing but some physical, visible changes that are created by the microorganisms. And I'm sure all of you have seen this in some portion or the other, and it doesn't need to be essentially cultural heritage. It can be buildings, and you will see it. And what happens? So this will give rise to an aesthetical damage. It clearly look bad, and this whole process that you see is happening is called a biogenic damage. Now, okay, let's not just blame the microorganisms, okay? Because we also have big issues like, and I'm sure all of you are very familiar with the picture of the temple with roots. It's Angkor Wat, and it's an ongoing process. It's an ongoing debate whether should we remove the microorganism, should we not remove the microorganism, should we make it clean. But you need to understand that when we have the roots of the trees, which are so deeply embedded into a structure, like, so that causes a lot of cracks, fissures, which in turn gives rise to microorganisms, which I will explain what I mean in the next few slides, because they will go inside the crevices, they will go inside the cracks, and that's where they will thrive. But as you can see, before the microorganisms colonized the area, we had roots of the trees, and they are really strong roots, so you just cannot uproot them. The second one, again, something that is very, very known to us is pigeons. They just create ruckus, and there is pigeon poop everywhere, which is very high in nitrates, and it's really it just gives rise to lichens. It's like the perfect environment and the recipe for lichens to grow. And in addition to pigeons, we also have small animals, burrowing animals like rats, mice, sometimes rabbits, but these are always there, but of course we can see them. That's why we classify them as microorganisms. And so before we start understanding microorganisms, we need to understand how they grow. So when you have microorganisms just covering the surface of any object, it's called an epiphytic growth. But when the microorganism starts growing into crevices, into fissures, that's when we call it chiasmolytic. But when the microorganism has finished going just a few centimeters, like a few bit, like inside the substrate, but it's going in quite a bit, like a few centimeters, that's when it becomes an endolithic. So what technically happens is once the microorganism starts becoming an endolithic kind of a variety, there is a big problem that, like, you know, they will use the place, and finally what will happen is there will be a mechanical decay, mechanical weathering, where where a part of that substrate is going to break, it's going to come out. And this kind of ecology also clearly depends on where you are. Like in a more moderate type of climate, you will find more epiphytic microorganisms, but whereas in tropical, subtropical areas, you will find more chasmolytic and endolithic microorganisms. But we need to remember that they don't use the substrate just as for protection or just to stay there. When they start going in, that is also because they're looking for nutrients to survive. Okay, so this is a very like a quick thing of what kind of microorganisms that might affect the cultural heritage. So the first thing that we have is a light dependent growth. So these are your algae, these are your cyanobacteria, these are your lichens. Okay, so now cyanobacteria and algae is something that we have, and even I think lichens, if you know how to observe them, you will see them, like it's not difficult. But okay, cyanobacteria, and what happens is they look dirty, they just, like, there's major biofouling, but we know that this is a lichen. Okay, so the characteristic difference between between a algae and a cyanobacteria is how they live. They both take off the calcium, they both dissolve calcium carbonate, and they, by producing organic acids. What cyanobacteria does is they also cause a black patina to occur on top of the surfaces. And the and one point of cyanobacteria is that they can live in extreme environment. Like, so if it's really cold, it's not like they're going to die. They are just going to shrivel up, and the moment they find their nutrient, like say sunlight, they're just going to sprout again, which is a little different from algae, where algae needs ample sunlight to survive. They both do mechanical damaging. This is not something new. And they both grow. What they do is they start colonizing they start going from epilithic, where they're just on top, to endolithic, where they start growing inside. And as I said, so this is a part of soiling. Okay, so then we have nitrifying bacteria, inorganic bacteria, which is sulfur oxidizing or nitrifying bacteria. Now, what nitrifying bacteria does is it dissolves the calcium, and it's both sulfur and nitrifying bacteria, they dissolve the sulfur. For nitrifying bacteria, what they do is they oxidize with ammonia, creating a soluble calcium nitrate, which at the end of the day leaches out the calcium carbonate. So when you look at it, you will think it's either dirty or it's something, but it's all inorganic, because they are not really taking any material from the stone. What they're doing is whatever impurities that they have in the atmosphere, that's what they're using to create food sources and then propagate. The second one, the last one that is very common is fungus, and we know what fungus is. Okay, now it is an extremely resilient form of microorganism, and they can survive extreme dry temperature and in a high UV, when there is high UV light. What they do is they dissolute the calcium carbonate by secretion of acids. Okay, and it's very easy to understand once you like, it needs some time, but once you train your eyes, you can automatically see the colonies of fungus growing. So they will be black, or they will be dark gray, or they will be brown, or sometimes they're even yellow and reddish. And what they basically do is they do flaking. Flaking means you will have portions of the wall or portions of a structure which is slightly, like, you will see a depression, and then you will have discoloration of the Sergio, can you hear me?
Yes, I can hear you.
Okay. Okay. There is
Okay,
discoloration.
I will take profit of this interruption so I can read the chat. We have one question here from Ole, very
Okay.
participative. He is asking, that was in the previous part of your presentation. He was asking if human can be an agent of decay.
Of course, we are the biggest agents of decay. There is no doubt of that. Like, look, I mean, without sounding pompous or anything, but fossil fuels, automobiles. Then you will have in
Tourists.
a tourists spitting, littering, like everything. We just keep on adding stress on the monuments, and of course there is a big problem where we actually what we do is when we carve our names or put a graffiti on the wall, we are using what we are using a chalk or we are using some other material to carve it, right? So there is an interaction, and these microorganisms are damn smart. What they do is they immediately grab hold of whatever they can and they start destroying what is there. So yes, we human intervention is huge. And sometimes what happens when we are talking about human intervention, sometimes when we are conserving the uh, um materials that we use are extremely harmful for this, because they can just leach out stuff. Instead of making it better, it can just make it worse. So
Very
that's
true.
that. Does that answer his question?
Yes, I believe so. So thank you.
Okay. So I'll go back, and when you have fungus, the fungus plays the substrate that the fungus is on plays a very important role, and limestone is a perfect thing because it's porous, no? So they will just keep leaching out the calcium as much as they can. Okay. Now we have this curious case of lichens. Now lichens is part fungi and part algae. Okay, and they can grow anywhere. They do not listen to the temperature. It can be hot, it can be cold, it can be humid or not, and they can stand extremes of temperatures. Like what will happen when it becomes really cold? Again, like the cyanobacterial, they'll just curl up, and the moment there is some kind of nutrition, they'll just sprout. So many times when you go to when you go to one of the Roman ruins, you will see it is a seasonal thing. You will not see them always. Also, the thing is, what helps them survive is bird droppings. And this is a serious case because they have nitrates in the droppings. We have three types. We have three types of lichens. We have the crustose, the foliose, and the fructicose. Now, the fructicose is actually the worst because their roots, the hyphae, the rhizines, as you can see in this picture. That's the roots. They really can penetrate inside the substrate. And these are some kind of examples that I'd like to show. The one with the orange one, not the orange one, the yellow one, these are very common. This is, I think, Cladosporium, very common in monuments. Okay, so the next part that I'll come to is what happens to this when there is degradation or deterioration. There are multiple reasons why we have this. One is the effect of salt. Now, these are crystals, salt crystals. You need to remember the stone is porous, right? So due to the air pollution with the sulfates and the nitrates, so what happens is these crystals start settling inside the pores. Now, once the pore is covered, they start settling on top of the monument, and they start leaching whatever can be leached. The other part, okay, the main culprit of this is air pollution. The other one that we have is also because of soil, because sometimes what happens is when we are using it for um, conservation, the soil that we use, the material that is inside the soil will have salt crystallization, and they'll settle. You cannot, like, suddenly you cannot remove them. So when alveolar weathering is a part of effects of salt. So when there is salt crystallization with the wind, it gives to alveolar weathering. Because you can see in this particular image where, have you seen how this rock, it looks like cheese, like that, because certain portions, the porous portions, have been weathered. Um, the second one is, okay, the biofilm formation. Now this is how do I say, this is like a perfect environment for microorganisms to grow. Okay, so what happens is there is a formation of this called extra polymeric substance. We call it an EPS, and it's like a mat, but when you see it, it's like a, it looks like a carpet, it looks like a mat. And what they do is it not only protects the microorganisms inside, it also generates nutrients, and they colonize more and more area. And these biofilms form a protection, like a physical barrier to any kind of disturbance that might happen from outside, and this helps the microorganism thrive in this. And this is particularly the reason for biofouling. And these are all simple. So you have discoloration. Now discoloration, a lot of people are of the opinion it's aesthetic, but it is actually, it is an aesthetic problem, but it is caused by carotenes, or by the fungus, or by the cyanobacteria. And that's why there's discoloration. There's also discoloration because, and especially the picture that I have over here is of the Taj. We all know that it's changing color. It used to be white, now it's yellowish. It's also because sometimes you have the air is, due to the air pollution, it's really bad, and it forms a kind of patina. Then you have soiling. Soiling is mostly because, again, it's for water, and it's from metabolic waste of the microorganisms, and this is helped by any kind of bird dropping or animal dropping. Sugaring and cracking is very simple, where, you know, the statue, there are cracks, or, you know, there are certain areas where the statue is supposed to be smooth but it has become rough. But these are again actions of the wind or the sun or anything. So now this was what I had done for my master thesis, but I'm going to make a quick presentation. So what over here, I'm going to speak about three particular problems that we had, three pathologies that we'd like to call. One is salting, one is staining, and one is the biofilm formation. First and foremost, we need to remember, when we are working on this is a multidisciplinary technique. So you have many techniques to confirm or dispel what you already know, or it can give you better results when you add one or two techniques. So the first thing when you go to study that we do is we study the change in color. Now, we can use a handheld digital microscopy, because what it does is, when you're looking at something, and this microscope especially, you can look at the substrate in in the visible range light and also in the UV light. So when you see it in the UV light, can you see the areas that are pointed? You will have slight fluorescence. Similarly, so we know that there is some microbial actions, there's some problem that's going on there. So the next thing that we do is we look at colorimetry. Now, if you see the black triangle, the black triangle is the non-altered area. The non-altered area means, okay, of course it's altered, but not to a certain extent. So you can see that they have been plotted elsewhere, like the non-altered line is almost on 0. So let's come to salt efflorescence. Now this, when you have salt efflorescence, we have a phenomena called scialbatura. Now scialbatura is nothing but a patina, and this patina is because of the leaching of the the calcium carbonate. And what is salt? Salt is basically, like, you know, it's the two calcite salts that you will have mostly are wedellite and weyelite. Okay, it's just with water molecules. And the picture that you're seeing is actually of marble, but when you look at it, you can see how rough it has become. It's just that the calcium carbonate has been removed, it's been leached, and there's a patina that has formed. And scialbatura, the patina can move from light red to yellowish, and that's exactly what has happened. This is an X-ray diffractogram from X-ray diffraction, which basically in complete layman's term is like we see the crystal lattices of the molecules. And so that I understand, and I have complementary techniques. I did Raman spectroscopy and FTIR, where we have particular peaks for oxalates, and this is not something that I knew. It's something that you have to study, and it's bibliographic references, and previous researchers will help you do this. Let me come to the second pathology, and that's staining. So when we studied staining, now this is a portion of that the main limestone that had become unhinged. So we can already see that there is iron degradation inside the marble. Okay, so which is again confirmed with the X-ray fluorescence, because my iron peak is really high, and then subsequently with scanning electron microscope where I can see iron. So it's just a way of confirming what I thought. And we all know that when marble is formed, it's a metamorphic rock. So when marble is formed, there is some kind of impurity while it's being formed. So in this particular marble from the Eskimos anticline, we have iron degradation. Again, in the inset that you can see the image, these are the image, this is the staining that we saw. Now we need to understand, and as I said previously in discoloration, keratins are one of the main components for discoloration like this. We also know that there are certain microorganisms that create these keratins, and these two were just complementary techniques to look at the peaks and say, okay, I have carotenoids in it. This is the most important one. This is the biofilm formation. Like when you look at it, it looks like a carpet. It looks like a carpet. It's smooth and sometimes it's slimy. But how do we actually understand whether it's a biofilm formation? We need to figure out if there are organic compounds, and this will be in form of oxygen, carbon, nitrogen. If these are present when I am seeing the substrate under the scanning microscope. This is another one. This is a very interesting slide, because when you have biofilm formation, and when I'm using a Raman spectroscopy, what happens is the laser doesn't reach the substrate. So there is a reverse curve. You cannot see any peaks on this. So, and this is a identifier of the presence of microorganisms. And these are some pretty pictures that we did. And the first image that you can see is the substrate, which is almost being eaten up by the microorganism. And the second one is where the microorganism is actually, like you can see it breaking slowly, allowing mechanical decay of the substrate. Okay, and as I said, the biofilm is not just microorganism, it just traps everything. So it's not particularly necessary that you will only find microorganisms. You'll find many things. So the first one is not a microorganism, that is a diatom. And the second one is actually algae, because algae has very particular morphological features, and this is what algae looks under microscope. Okay, now let's come to the microbial point of view. Okay, so when you study this, this is what you grow. This is what you can grow. Now, when you grow the microorganisms, you can only probably grow 1% of the population of the microorganism. You cannot grow the 90, like the 100% population. They will not grow because they have a mind of their own. They will do what they want and they will not grow. Okay, so this is some filamentous fungus, some yeast, and the rhodotorula that you can see. Can you see the color? It's the same thing that we had found in the staining, and it's full of keratins. Then we'll come to the study. It's we call it the next generation study, because it helps us study the metagenomic DNA. Now, what is that? Metagenomic DNA is basically studying the entire microorganism population in the environment of a given space. So this is how we study. I'm not going to get into this because this is quite like it takes some time. So this is what we have is of prokaryotes, which is your bacteria, and this is what we have for eukaryotes, which was basically fungus and yeasts. And these are some of the stuff that we found. Now, thanks to literature review, we already know that Conosporium or Nufia or Trimatostroma are really, really dangerous to microorganisms. But we also know that Rubrobacter and Staphylococcus, these are the most common kind of bacteria you will find. And when you see Dirina is a type of lichen. But unfortunately, I couldn't study the lichen. But Dirina, when I find Dirina, I know if I do lichen studies, I'll definitely find some stuff. And after we come to this, there are two very important questions that we need to answer to ourselves. And the world of researchers are somewhat divided in this. One is, are microorganisms beneficial for cultural heritage? And the other one is, should microorganisms be removed from the monuments? I mean, I guess even Sergio in his presentation spoke about corrosion. So it's an ongoing topic of discussion, I think, across the field. And yeah, I particularly like this thing. And I would like to thank the Laboratory Hercules in Evora and my professors and the postdocs, because I mean, whatever the case study that I presented was done with their help. And yeah, these are the picture credits and bibliography. And thank you.
Thank you, Shri. Thank you so much. That's a hell lot of bibliography. You did your homework. Okay, I will remove your screen. Okay, you can stop sharing the screen now, so maybe we can get your webcam to work again. Oh, there you are. Okay.
Yeah.
So we are open for discussion, and please type in your questions or comments in the chat so we can talk about it. Thank you once again for the presentation, Shri, and about removing the microorganisms from the surface. Is there a protocol or some kind of, I don't know, a booklet, a handbook? Should I remove it or not? Or something like that?
Oh, no.
Definitely not.
Every case is different. Okay, now if you have to take Angkor Wat, for example, like, what are you going to remove? The trees, the bugs, or the microorganism? Like, who comes first in the removal process? Also, if you remove the trees, are the monuments going to stand? Like,
Yeah,
it's a very ethical question, in my opinion.
Yes, for the metals, as I said, well, my position is that the corrosion and that layer, let's call it patina, because then we have the same terminology for both things here. The patina is part of the object's history, as the same way it is a part of the monument, the stone monument. But you have to prevent it from further degrading the material, otherwise you will lose it. It's the same for metals. When you have that severe corrosion, you have to stabilize it. Otherwise, you'll just lose the object forever. So I believe that I'm not an expert with stones. I know a tiny bit of it, but I believe that there is a certain point, like a threshold, where it starts being very dangerous for the monument itself. And then you have to intervene, right?
Yes. The thing is, the intervention bit is a little, how do we say it? Because the thing is, initially, they used to use biocides which were really strong. So what they were doing is, even if the microorganisms were not leaching or spoiling the surface, the biocide was. Okay, so it was and the thing is, this is a catch-22 situation. Yes. So you do not know, I mean, you cannot say, okay, I removed it, this is great, and then go, oops, I shouldn't have removed it.
Like, yeah, exactly. That's how it works. There is a case with the Vatican Museum. They were trying to clean the statues from the garden. They were using some product specially designed for it that was very toxic, and it was killing the plants around. So then they started using some alternative, some bio-green product that was experimental, and it worked. It was not a toxic, and it was working perfectly well and cleaning all the statues, like removing all the damaging microorganisms from the surfaces. And
we have a question that says, should it be removed in moderation? Now, yeah. What is moderation? In my opinion, it's again, this is a very I think this argument is a very philosophical one. In moderation, do you want to do patch test, or do you want to not do patch test? Because I'll give you an example. What has happened is, when we went to the Geronimos monastery, you can see certain areas which have been cleaned, and they say they use 2% Preventol. But is the 2% Preventol bad or good, because the places where they have used Preventol is clean and it's all nice, but the surface is spoiled. As opposed to places where they have not used anything, I can still see the intricacies of the of the monument, but the only thing is the microorganisms. But at least with the biofilm formation, they are not damaging the surface, the substrate, because once the substrate is damaged, it's gone. Like
Yeah, this is a good strategy.
we are just enabling weathering and erosion.
Yeah, it's like when you deal with laser cleaning, you have a small patch of the object where you test it and then you see how it behaves on the material. Well, everybody's thanking you
Professor
for the
Gigante asked a
yes,
question.
yes. I was going to read his question now. Everybody's thanking for the presentation. We have a message from Daria, from
Welcome.
Russian, from
Very
Helena,
much.
and also from Maria Isabel. And Giovanni is asking, he's also congratulating you for the presentation.
Thank you.
And he's asking what is the strategy to detect if a deterioration is chemical or biological?
I work with microorganisms. For me, everything is biological. I mean, the first thing I do is want to see what kind of microorganisms are growing. But to answer the question, if I mean, for most of the places, what I did is, because I was just lucky to have found that fragment of marble which was dislocated. But when we didn't, what we did was we did handheld XRF. That was the only way I could understand the chemical composition. But then I already had literature which said that, and it's a marble, it's an estromos, it's a marble thing, marble monument, right? So I, I went with the mindset like to study the chromatic alteration and to study the microorganisms. I didn't like, this was something that I added to my study where I did SEM because I was lucky to do SEM. I was lucky to have these samples.
So thank you very much. Thank you very much for your time. Thank you, Shri, for your presentation and for
And
being
thank you
here.
to you too.
Okay.
Thank you.
Bye.